Okay, in the probability we have something called experimental probability. Sometimes when people are producing something, for example phones, they also produce faulty ones. That means they don't work. For example, maybe 1 in 1,000 iPhones are already broken inside, the chips are damaged even when they produced, before they get used. Or maybe not 1 in 1,000 but 1 in 4,000. Or depending on what you're producing, sometimes the fault rate goes up or down. So there's more chance of something being faulty. So of course factories, they try to make it as less as possible, but they also want to get a chance of things going wrong, because each month, of course, with the faulty ones, they're losing money. For example, in some sectors, the fault rate is higher than maybe 2-3%, but in some sectors, it is, for example, if you're only producing paper, maybe it is maybe less than 1% of chance that you will not produce the proper quality one. So it depends. So we have something called experimental probability. This is different than the theoretical probability. For example, you probably know from the dice as well, when you have a dice. In theory, right, and theoretically, you have 6 sides. So getting one side is 1/6 probability. This is the case in the dice, but what happens when you get an actual dice and roll it on your own, or even dice on my phone? Well, what happens if I don't get 1/6 every time? I don't try 6 to get 1. Let me see, for example. Okay, I need to get 1. I tried once, twice. Okay, now I get 1. But maybe next 12 times, maybe 20 times, I will not get 1. So when I experiment with stuff, it changes. Okay, so that's called experimental probability. Each time I roll a dice, I call it a trial. I try. And my experimental probability, or relative frequency of something happening, frequency meaning how often that takes place, is number of successful outcomes. Successful, or too many outcomes. Total number of trials. Let's say that this is a theoretical probability. I would like to reach that by doing it an experiment on my own. You can also do it at home as well. Okay, so now I'll try and then I'll get what I have. Okay, and I'm looking for the ones. I'll start. Okay, I get 5. I get 3. I'll do it maybe 10-20 times. I get 5. I get 2. I get 4. I get 5. I get 3. I get 2. I get 1. I get 5 again. We'll see how I get so many 5s. I get 6. I get 5. 3. 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Um, 4, 3, 5, 2. Okay, out of I think out of 20 trials, total number of trials is 20. I tried 20 times. Number of successful tries, meaning that I need to get 1, is only 1 actually. Look, out of 20, I only get 1 once. So my experimental probability or relative frequency is 1 over 20, but in theory it should be 1 over 6. Okay, so in real life, as you know, that might be different. In real life, if I want to get the theoretical result as close as possible, I need to try 50 times of the possible outcome, 50 times larger number. What do I mean? The possible outcomes are 6, right? Because I can get 1, 2, 3, 4, 5, or 6. So if I try this, if I multiply it like 50 times, which is giving me 300. If I have 300 times, at least, if I try at least 300 times, I'll get close to, in theory, 1 over 6, which is the real probability. This is for the dice. If I'm talking about a coin, right, coin, head. If I get the Danish coin has a hole in it. So since for coin it's 1 over 2, I need to try 50 times more, which is 100 times. I need to flip a coin 100 times to get a close result as 1 over 2. It doesn't mean that, like, if I only try 50 times, I may or may not still get it. But to get as close as possible, I need to try it 100 times. Of course, more tries give you even more accurate result, because if you try, let's say not 300, but 3 million times, you'll probably get very, very close to 1 over 6. Because that's how it works, how the probability works. Like, think about the chance of winning lottery, right? Of course, more tickets, closer, and more chance. Or if you try more times, well, the chance is still the same actually. But yeah, okay, well, that's some other example. But it should be getting closer to your real possibility of getting things. Okay. Let me show you how to do these examples. It's not so hard. Let me get a new page. This is a factory, and then they're testing their products, and they're finding the faulty ones. So that's an actual data, okay? So this we can use instead of the theoretically making wrong. And also for factories, that's how they decide, right? Because it's not like throwing a dice. They don't know the faulty rate, they just test it. And they get a sample, and then they test it out of that sample, and then extrapolate. For example, iPhone, if they produce 1 million phones a day, they don't test all 1 million phones. Maybe they pick randomly 2,000, and then they test those 2,000, or maybe less. What is the experimental probability here? A circuit board being faulty on Monday. Okay, so Monday, 11 faulty out of 220 produced. So it is 1 over 20 chance. That's the experimental probability of being faulty on Monday. What's the experimental probability of circuit board being faulty over the whole week? So what I do is that I get the number of tested whole week, meaning that I add Monday plus Tuesday plus Wednesday plus blah 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 all the way to Saturday, and then I get the faulty ones up here. 11 plus 8 plus 5 plus 8 plus 12 plus 6. So in total I have 50 over 100, which is 1 over 24. This is the experimental probability. This is the real data. There were 1,000 circuit boards made altogether last week. How many are likely to be faulty? Okay, that's why we are doing this. This actually have a physical meaning as well. If you're making 10,000 circuit boards, you don't test all of them, you just some of them, and then you use this data. 1 over 24 is faulty, so over 10,000, if 1 over 24 is faulty, you'll get, where is my calculator? There's like 416.66, which is 417 can be faulty. That doesn't mean that it has to be faulty, but it is the most probably. It's either like, around this number. It's not magic still. Of course, you may have it days with like maybe 440, but this is number, or weeks with 440, but this number is close because you have a kind of the percentage holds for the rest of the week as well, for the rest of the data. That's why you're keeping the experimental probability.